So what we did, just to remind you, last time we solved the following problem. We used the Smith chart to transfer an impedance from BB prime to AA prime. When we say we transfer an impedance, what we really mean is that from an input impedance, from the load rather, which is also the input impedance at BB prime, we go towards the source, and I am at AA prime. And then when I look now towards the load, I see an equivalent impedance there, which is here, what we would normally use on paper. You see this formula. That's how I would calculate that input impedance at AA prime from the load, and this is all normalized, from the load at the end of the line and from the distance from the load. So that's the formula. However, on the Smith chart, to find this, I have to follow this process. I'm only moving along the green circle, which represents movement along the transmission line. I move in a particular direction. There are only two possible directions: counterclockwise, the purple, and clockwise, the blue, the arrows. And I move along the direction that really tells what I'm doing physically. Now, in this problem, if your load is on my right hand, now you see them reversed, I think, at least I do. I don't know how you see those, but if your load is on my right hand and then my source is on the left, and I move from the load towards the source, that therefore on the Smith chart, it shows along the yellow rim, and then says wavelength towards generator. And that's the direction I take because it shows me with an arrow the direction. So I move from ZN, you see the arrows, the little arrows on the green circle that shows me which direction I'm going. And I stop after I move by whatever distance is the length of the line that has been given to me, which is 0.3 lambda. So today, we are going to solve some similar problems. And in fact, that you will have to do in the second part of your homework. You will see your homework for this week. It asks you to find an input impedance, the individual homework, when you have two lines that are connected in parallel because they share the same voltage. And then it asks you to find the input impedance at the input port using the Smith chart. So you have to transfer impedances. So we are going to solve now another problem, and I'm going to start on a new, just for today's lecture. And also what I was going to do is take this Smith chart, which I like, copy it, and then go to my notes, not these new notes, the new notes for today, and then paste it. Okay, and then I clean it up. So I will remove that. Okay, I don't need those things. Also, these were from previous times. All right, so the problem today, the example rather, of the problem is the following. The example rather, we're going to solve, not the example of the problem. Okay, so let me see. I need to write here. All right. So example. One. Also, I wanted to tell you, I do not prepare this. I mean, I know what examples I want to solve. I don't prepare the solution ahead of time, because if I do that, it's going to be so much complexity of all of the lines on the Smith chart that there is no way that you are going to be able to understand the process. That's why I'm doing now things in real time, and also gives you time to see what I'm doing and take any notes if you want. But primarily because if I do the solution, then it's gonna be so many lines that it will be difficult to for those who try, for you who tries to learn it, who try to learn it. All right, so the problem is the following. So we say consider the following example, the following problem, the following transmission line. And I'm gonna do a similar to the homework, but not the same. So the transmission line here is as follows. First of all, I will do it in steps. I have a line that is given, not this one, there, and then duplicate. All right, this line has two impedances at different locations. So in fact, many times you will see the line split in two pieces. And in this case has an impedance that is like this, is connected here. Oops. In series. That's impedance 1. And then it has another section of the line. And then here, just to see that the line is the two wires running in parallel, usually I will do this. The thin lines are the way we use them in circuits. They don't mean anything. It's just how we lay them, we lay the circuits down on a paper. Practically, whenever you have thin wires like this one, as you know from circuits, have no length. So practically what that means. That means that if this is the points B and B prime, and this is a point C and C prime, then the equivalent, and then it's the equivalent to that would have been something like this, where you have a circuit, for example, and you have a series resistance, and then you have an inductor, and then you have a capacitor or something. I mean, I'm trying to make it. Now, we do it like this, all right? That's how we write the circuit, and then we put here the source. This length means nothing. There is no physical length associated with it. So this point A and this point A prime are identical. We just have physically to lay it out like this to use this length. You got that, all right? So another way of avoiding this will be to do it, which we don't, to do it like that. We don't do that. So we enter in circuits lengths that really mean nothing. It's just a way schematically of connecting points that are identical. They have the same voltage. So point A and A prime are identical electrically speaking. So considering this, now the same thing applies here. Whenever you see me doing two thick lines, which is a transmission line, and then do a thin line that implies points B prime and C prime have the same potential. The voltage drop between B prime and C prime is 0. However, on the other side, I have a series element. So you remember that. Now, whenever there are thick lines, it implies that there is a length involved, electrically speaking, always electrically, all right? So thick lines show electric lengths. thin line, so no electric length involved. Okay, just to keep it in mind. So, and then I assume that here is Z naught, here is Z naught, and then I assume that at the end of the line, I have, let me see, here, I have a load. And this load is ZL, ZL. And then I'm asking you to go to the beginning, so this is D prime. And then I'm asking you to go to the beginning of the line A prime. And let's assume that you put a source here. Ideal. V naught. Let's assume V naught is 1 volt, just for simplicity. And then I'm asking you to do two things. If, for example, I could ask you directly, find input impedance at AA prime, and I will just indicate that, all right? And then 2, find the current, the current at A prime, the current that enters the line at AA prime. So we know that there is going to be a current like this entering here, okay, total current. This is the AA prime current. And then the input impedance at this point will be Z in at AA prime. Okay. And I'm asking you to do oops. I hope okay. I see. Did not somehow find the current. I did not take that. The current at AA prime. So here I have to enter an input impedance. All right, and then the current here would be I at A prime. Okay, now what do I give you? I always telling you, always in a problem like this, write down your data, number one, and then write down your formulas. All right, always. You're not going to try to solve anything without writing. First of all, I also would rewrite the problem. I always do that whenever I have to solve a problem, even if they give me a figure in the problem, I do it myself because it helps me put the whole problem here. And then let's assume here I'm asking use Smith chart for this. Use Smith chart. That's what it means, not South Carolina. It means Smith chart. All right, and now I have the solution here. So what am I gonna write? What is given to me, and probably what is given to me, they would have given it before I write solutions. So I will put everything down here. Assume in this problem, that's what the problem says, assume the following. That ZL is say 50 minus J 100 ohms. That Z1, let me also move this for a second, I'll eliminate that because who knows how much space I need. Z1 is, well, minus J, whatever, minus J 50 ohms. And then D1 is 0.1 lambda and D2 is 0.2 lambda. Okay, so that's all that I'm giving you. And before you write the solutions, it's critical that you write down what I'm giving you, all of these. Also, to notice here, I have not given you a characteristic impedance, which I will. And of course, I will have to give you characteristic impedance Z0 to be equal, say, to 50 ohms. And I give you lambda, which you don't necessarily need, since I'm giving you the lengths in lambda. That's where I will stop. A lot of times, people give lengths in lambda. If they give lengths in physical dimensions, then that implies that I would need to give you lambda for you to be able to use the Smith chart or anything practically, all right? But here I don't need to give you lambda. All right, so now solution. Before I continue, do you need any clarification in what I wrote?
Is D1 the distance from AA prime to BB prime,
Yes.
and then D2 CC prime to DD prime?
Exactly.
Okay, thank you.
Sure. So here, since there is a question there, it's this one. Okay. So now, what I will do, let's think of the strategy. I need to use the Smith chart. To solve this problem, I have to follow the steps I will show you. I will take this and duplicate it. What I noticed is that some of you, instead of you doing your own figures, you try to go immediately. I noticed that from the meter. And you go on my figures and then try. No, it's a bad idea. Even if you may lose a few minutes drawing your own figure, there is something important for the brain. I'm telling you. I mean, you think that I'm overdoing it, telling you how the brain works. Remember that it's like you use a transceiver in an iPhone. So you want to develop a receiver for an iPhone. Unless you understand how what your devices can do. In a transceiver, you have a filter, you have a low noise amplifier, you have a mixer, you have a another filter and the IF band. Okay, so you design all of this separately, and then you put them together, obviously, you integrate them. Unless you understand how your filter works, how the low noise amplifier can work, what it needs to work. If you don't understand that, you just take things, you throw them together to make a receiver, it's not gonna work. And so what we do as engineers, we take the components, we understand what each component can do if they are given to us, or we design them knowing what they can do, and then they put them together. So now, and then you have a receiver, and then somebody wants to put a receiver on a much bigger system. So unless you understand how your receiver works, how are you going to put it in doing anything with that? The same thing with us. We take the brain for granted. We have an understanding that the brain somehow works in miraculous ways. And then we try to make the brain do things that the brain cannot do. So the brain learns in a particular way. When the brain goes into a process where you lay out something, this process by evolution is important, and the brain learns like that. So if you use my figure that I put together and I understand it, and you go on that and quickly you try to do things, I'm telling you, 90% of the time you're gonna miss something. 50% of the time your solution is gonna be totally off. And only those who have really been successful in solving the problem well are those who take a little bit of time to repeat it. So that's what I'm asking you to do for those who don't do this as practice. Okay. Now, I'm gonna first of all do the following. I will transfer, because the way it is, I cannot do very much. all right, to find the input impedance in the from. I will transfer ZL from DD prime to CC prime. So I will come here as a step and find this impedance. Z input at CC prime. The moment I find that impedance, then I will take this part of my circuit, duplicate it, and put it here. And in this part of the circuit, I will replace this section of the line with the impedance I found. So what I will do here, I will move this out. I will put the impedance I found here. I will use a different color to remind you that I have calculated that. And that's my Z input at CC prime. And then I will calculate, when I do that, I will calculate the combination of these two. How do I calculate the combination of these two? How do I do that?
In series.
Yes, these are in series. So what I will do is that I will find a total impedance here, Z total, to be Z1 plus Z in at CC prime. So I'm outlining now the way I'm going to solve the problem. And then, having done this, I will take this part of my line, I will copy it and paste it, and I will replace the two impedances by one. And here at the end, I'm going to put this impedance, which is going to be Z total, which I computed before. And then I will also transfer this impedance along this line. And by transferring this impedance, it's going to give me the input. All right, you see the process? That's how I'm going to solve it. You solve it like that, both on paper, and you solve it like that using the Smith chart. So let's try to do this by using the Smith chart to follow this process for the solution.
So just to summarize, we're first finding the impedance of the C's and D's, and then the impedance of the A and B.
Yes. First of all,
Okay.
you find the impedance at CC prime to replace that section of the line. Then you put a series combination of this with Z1, and then you transfer this to AA prime, and you're done. Okay, I mean, I repeated what you said.
Yes, thank you.
Yeah. All right. So let's prepare ourselves for the Smith chart. What do we need to do to go to the Smith chart? Let me ask you this question. What is it that I need to do which I don't have done, which I don't have here, which I have not done it yet?
You need to find the magnitude of the reflection coefficient of the load.
I don't need the reflection coefficient at this point. I need something else more fundamental to go to the Smith chart. What do I need to do to go to the Smith chart?
You need to obtain the normalized numerical value of ZT.
Excellent. I need to normalize impedances. Remember two important things, two very important things. Number one, Smith chart needs all lengths in wavelength, but we do have those. And the Smith chart needs all impedances normalized, which we have not done yet. All right, so we need to normalize the impedance. So I'm writing here so you remember it. Normalize impedances. All right, which means I will have to take the impedances that were given to me and divide them by Z naught, which is 50. So ZL normalized, I could do it here as a matter of fact. That's where I would normally do it, next to my data, is going to be 1 minus J2. And then and of course, it loses the units. All right, the moment I normalize it, excuse me, I normalize it with respect to Z naught that is in ohms, then I lose units in the normalized entities. And then Z1 is minus J, all right? I need these. Without those, I cannot go to the Smith chart. All right, so let's start let's do step, this is step 1. And this is step 2. All right, step 1 means I transfer the impedance and I put them in series, I sum them up. All right, let's do that then on the Smith charts. So I will do here, it's gonna be step 1 on the Smith chart. First of all, I need to find Z input at CC prime. So I will start with ZL. I need to find ZL on the Smith chart. ZL, according to my notes, is 1 minus 2J. Remember I told you how I'm gonna do it fast? 1 is here on this circle, and minus 2J, minus 2, minus is below, minus 2J is gonna be on this circle. So I have to intersect these two. The intersection of these two circles, so let me use another color so you can see it. Oh no, this one, a different one, this one. So I'm intersecting this circle, which corresponds to 1, real part 1, with this circle that corresponds to minus J2. All right, the reactive part is going here. In fact, 2 is here, minus J2, 1 is here for the real part. The intersection of the two circles is this one. Okay, so now this is point ZL, normalized. So let me write it here. So that's ZL. Now that I found ZL normalized, I will erase the other circles because otherwise it's going to get too busy. All right, that's my ZL normalized. What do I have to do now? I have to move it on the line as what I have arranged to do as step 1. I have to move this to go to CC prime. From ZL, which is a DD prime, I have to move to CC prime, which means I have to move on the constant gamma circle, which is like the circle of the transmission line. I have to move on this, and then I have to stop after 0.2 lambda. So let's try to find the circle of the transmission line. How do I find the circle for the transmission line? Is the circle that has the center at the center of the Smith chart. So this is gonna be this circle. The center is here, the center of the Smith chart, and it goes through this point, ZL. So I'm gonna write a circle that looks like this. It's not exactly, but I will place it the moment it's there. You see that? Maybe I need to use it a little darker. There. And then I increase it, but I have to also move it. Okay, that is the green one, is the circle of my transmission line. Then I know exactly what it is if I know the load. So this circle. Question number 1, how would I find the reflection coefficient on this part of the line from the Smith chart? If I want to work, if I were, say, for example, let's assume that I had asked you to find the reflection coefficient on this line, somewhere in this line. Let's assume that I consider a position here on the line. I'm going here. And that's a random position on the line. And I want to find the reflection, the magnitude of the reflection coefficient there. How would I find it from the Smith chart? Do you remember? Who can tell me? Any takers?
Don't you draw a straight line from the left or the right side of the circle down
Yes.
to
Yes, thank you. That's correct. So you draw this straight line. All right, that is perpendicular. And then I think that's, I don't know whether that's perpendicular. I'm not sure now, but in any case, let me see. Let's assume it's somewhere there. Yes. And then I look at here. I am looking down at this line that says reflection coefficient here. And I'm reading this number here, here. And this number says that its point gamma on this line is 0.6, approximately 3, 5. And somebody can check it out if you want. But the magnitude, I found the magnitude without putting down any complex numbers. All right, so the magnitude is about that if I wanted to find it. But now what I need to do, and let me also make that so it does not interfere with your visually. So what I want to do is move from ZL towards the generator. I remember that moving towards the generator means moving along this. So I move along this direction. And I move on the green line along that direction by 0.3, I believe. Did I give 3? 0.2 of a wavelength. So how do I do that? I draw a straight line from here, there, and I'm measuring on the outer rim, on this purple rim that you see. So I'm going, this purple rim here goes like that. Okay, so I'm going here to read what number it is there. I want to look at what number here. And what I read from this number there is, so here. What I'm reading is 0.3, practically 1, 2. So it's 0.312 lambda. That's where I am. Let me also erase that to make it point. All right. Now I want to move by 0.2. So I have to add to 0.312 another 0.2 that will make it 0.512. Remember that? So practically, if I add here another 0.2 lambda, which shows how far I have to move, that gives me, all right, so I will put this here to remind you that this is what I need to add. And that makes the total 0.512. So that's where I have to go and find myself here. I have to go here. To go there, I have to move along this purple circle. I have to move like that. And because it stops at 0.5 and then starts over again, I have 0.5 here, and then I need a 0.012. more beyond that. So practically, I need to move for another 0.012, which is going to be 0.01 here. But I need to move by this amount. 0.12 here. All right, this is point, just to put a different color to see, this is 0.12. Okay, and then I connect that point with the center of the Smith chart. That's not exactly connected. Okay, I need a straight line. There. And I find the intersection of this with a green circle and is exactly now here. So practically I moved, just to show you, like that. And I do that for me to know which direction I have moved on this point. When you do more complex things, it's important to have that. It's helpful. Otherwise, you don't know which direction you have moved on the circle and which circle if you have multiple ones. Okay, so now I found this point there, which is, okay, this point here is Z in at C prime. Okay, so now to show you, let me make it smaller. All right, so you see the Z in and C prime. This is practically your Z in at C prime would have been here. And I found it. Then what do? I have to add to this in series. So I have to combine that in series, if you remember, to this stage with Z1. How much is Z1 normalized minus J? So I have on the Smith chart, so I remember Z1 is minus J. I have on the Smith chart to go to this Z in, CC prime, and add to this minus J. So the resistive part of this is going to remain the same. The reactive part of this is going to change. And here, as a matter of fact, let me write what I see for ZZ1 CC prime. I will read it also, so I know what I'm having. And here, in fact, I will extend this. I want to extend it a little bit. Here. There. And I'm going to write that to read it. This is equal. Let's try to read it together. Who is going to tell me what is the value of this here, this dot? How are you going to read this dot here? That is multicolor. What is the real part of this dot? Can you tell me from this close up?
Maybe 0.21?
Yes, it's close to 0.1. It's a little less. Maybe it is because it's, I will say 0.21. All right, so the real part is 0.21. What is the imaginary part? We read the, for everybody else, we read the real part, just to remind you, from here. You see that? From here. from there. That's where we read it. Okay.
Reactive part looks like 0.7.
The imaginary part,
Yes.
how much is it again? Point?
Looks like roughly 0.7.
0.7, yes. Well, not exactly 0.7, there is a 0 in there too. 0.07.
Oh, yes. Sorry about that.
That's okay. 0.07. So, which we read it from here. We go along, so the lines are almost like, we go along here, 0.07, correct. So it's, what did we say? I forgot that part. 0.21 plus J 0.07. Perfect, that's the input. To this one, what do we have to do according to our steps? We have to add Z1 in series. How much, therefore, is this one, ZT? So ZT, I will do it on the Smith chart. So ZT here should be minus J plus Z in at CC prime, which makes it 0.21, and then it's minus J, 1 minus 0.07, it makes it 0.73. How much does it make it? Is it 1 minus 0.07 will make it 0.083. Yeah, no, 93, excuse me. Okay, 7, 3, 10, 10. Well, yeah, so this one makes it 0.093. Do you agree? Am I right or not? No, I'm not right. It should be.
No, you're correct.
Pardon me?
Yeah, with the
Yes.
loss of the additional 0.
Yes, yes. There. Okay, so, and then it's negative. It's because it's a whole minus 1 plus this, it's all right. Minus 1 comes minus J. It's minus 1 plus 0.07, which makes it minus 0.093. So I have to find the number minus 0.93. How am I going to find this number? So it's down here, negative, you remember? Is the negative side of the spectrum of this Smith chart, which is below the horizontal line. So it's down here. I'm going to check here. So it's going to be, let me highlight it here. It's going to be, I'm going to go down and I'm going to stop at 0.09, 0.093, somewhere there. So to be accurate, I will probably 0.9, it will be somewhere here. And then I will go along this line, which is the constant reactance circle. I will, and then it's somewhere with they intersect all of them together somehow because they're so small. It's gonna be, the point is right here. All right, and that is going to be your Z sub T. ZT, normalized. And according to that, ZT normalized, whatever I found, is the real part is going to be 0.21 minus J 0.93. That's my ZT. Okay.
Professor,
Yes.
aren't you at 0.093?
Yes. Yes. Thank you. Thank you so much.
I think that it's right that the original one is correct. I don't think it's 0.093. I think 0.93 is correct.
Yes. So it's 0.93 and 0.93, it's here. Okay, so we'll continue. It's even better because I go so far away from the beginning, which all clumps together. 0.093, here. There. Okay, so now, what is the resistive circle? The resistive circle has to be 0.21. So the resistive circle is gonna be, it's all cramped in the beginning, but it's gonna be somewhere here. The red one. And the reactive circle is this. So my Z sub T is here. I'm correct right now, am I?
Yes.
Yes, perfect. So now, this is my Z sub T. Okay. Now what do I need to do? I will do it on the same circle, but for you, I would like you, in fact, in the beginning to probably use multiple circles so you can erase all of these lines, but I will do it on the same. When you repeat the solution at home, erase some of the lines or use multiple Smith charts so it's clean one right after the other. Until you get comfortable with many lines. So here I am at a different, if you see ZT is off my green circle, which means I have a different circle to draw for this part of the line. My grid circle was for this one, all right, the green circle. Now I have a different circle, which is this one, and you're gonna see it, I'm gonna do it with red. So it's gonna be the circle who has the center at the center of the Smith chart, but it goes around like this. And I will have to fix it, obviously, to look like a circle. More or less. Okay, something like that. That's the new circle for my second line, for the other section of the line. And to be able to find so let me write also, I was thinking that you should probably find it helpful to say here, this is, this is the, well, not that one, I got confused. Okay. This one is the circle for the line. So circle for transmission line between C, C prime and D, D prime. All right. And the red one, this one, is the circle for transmission line between A prime, and B prime. Okay, now I need to move on this line, which is this one, by a distance d1, which is 0.1 of a wavelength, which is this one. And I need to keep moving towards the generator. So I'm going to still move along this direction, all right, towards the generator. And since I have this one in purple to remind us, so it's going to be like this. All right, so I will move for 0.1 of a wavelength. Where am I right now? In terms of distance on the line, I have to connect the center of the Smith chart with this and come here on the outer rim and read this value. Okay, let's try to read this value. Is 0.3798 something, all right? I will say this is point. Could be very close to 0.38. Let me put 0.379. And then I need to add to this 0.1. So that's going to make it, I have to go and find the 0.479. So I will move on this line like this. And then I find 0.479. I'm looking at the outer rim to guide myself, the purple one. 0.479. Seven. I have to be somewhere here. In fact, I will have to connect the center of the chart. Put also here. I have to connect the center of the chart. 0.479 somewhere here. Okay, so I have to go for a bit more distance. And then stop here. And that's the end of my journey. This is exactly what I'm looking for. And this is Z input at A prime normalized. And how much is that? I need to read it. Is point, if you see on the real, on the horizontal axis, it goes here. So this is 0.1, 0.12, 1.4, say 0.1. No, 0.2 is there. It's 0.1, 0.12, 0.13. It's 0.13. And then, and the negative end is minus, I need to follow, see how I'm going. I'm going to follow this line. And I'm gonna read this, and it's 0.2 there, 0.22, 24, 26, 28. It's 0.2. Okay. So practically, we found using the Smith chart, then the impedance. Now, it may sound complex, but it's always the same. There are three things you need to do. 1, 2, 3, practically on the Smith chart. However, what it does is to give you the value of Z in at AA prime without making any calculations. So what I would like you to do, since we came very close to our time, follow this solution and compare the finding with your calculations that you would normally do. We're going to continue with that today in the afternoon with the problem solving session. We're going to compare the values, and then this is similar to what you're going to do for your homework. In your homework, you have two lines which are parallel. So you will have to find the impedance for each one of them, where they join, and then put those two impedances in parallel. So obviously you can use different Smith charts for the beginning. You can use the same, it's up to you. And then transfer that. So I show you the process here for a similar problem, yet not exactly the same, but I want you to follow, to show the steps the way I have them in your solutions. So we are going to look at this, do it using equations in the afternoon to compare. And then I want you to think of how I solve this problem so you can solve your homework. Any questions so far?
I had a quick question about like the second part. So is the current at AA prime just VO over ZN at AA prime, or is it something more?
The current then, I at AA prime becomes V naught divided by Z in at AA prime, but not the normalized. On the Smith chart, we find everything normalized. To find the not normalized value, you take the normalized, you multiply it by 50. Okay? Z here. So that's the one you put in the formula. And then you find the current as a complex number. Okay. Any other questions?
It's 9 o'clock.
Okay. Thank you. And I will see you this afternoon.
Oh wait, Professor, I had a question.
Yes.
It's okay that we don't get the exact same answers as you, right? Using the Smith chart. Just because like I noticed when I was doing it along with you with my Smith chart and like a little compass, and like my circles obviously weren't perfect.
That's okay, but you know it's going to be very close because the Smith chart gives you values down to a third decimal point.
Right.
So, you know, the errors you can make on the Smith chart are in the second. So if you do it carefully, not like me, where I went from 0.9 to 0.09. But if you do it carefully, then you're going to go very close.
Okay. Thank you.
Okay, so I will see you later. I will try to upload these today so you have them available before Friday.
Thank you, Dr. Good.
All right. Okay, take care.